Welcome to EDU World Space.
Let's find the partial sums for this series for part A. S1, well, that's just the first term of the series here. So go ahead and plug in n equals 1 up there. We have 1/2, that's our first term. S2, well, that's just S1 plus A2. So here we have 1/2, and then we do A2. So plug in n equals 2 for n. This is an, recall. So we have 2 over 3 factorial, and then go ahead and simplify this to get 5 over 6. Do we have enough to guess a pattern yet? Probably not yet. Let's go ahead and find a few more terms. S3, it's just S2 plus A3. So 5 over 6 plus 3 over 4 factorial. That'll take a little work to simplify, but there we should get 23 over 24. One thing I notice is that the numerator is always 1 less than the denominator. S4 is S3 plus A4. So that's S3, which is 23 over 24, plus A4, which is 4 over 5 factorial. And then here, this has to be simplified. So combine some fractions here, get a common denominator. We have 119 over 120. And once again, the numerator is 1 less than the denominator. So we have to guess a formula for this Sn. And whatever the denominator is, the numerator is just 1 less. So I'll just put the same exact thing, but then followed by a -1. So now I have to describe what's in the denominator. Well, when I plug in 1, I get 2. When I plug in 2, I get 6. When I plug in 3, there's a jump all the way to 24 and then to 120. These numbers look like they're coming from factorials. Here's 2 factorial, 3 factorial, 4 factorial, 5 factorial. So in general, it's just n plus 1 factorial. N plus 1 on top as well, and then that's a factorial there. So to verify that this formula is correct, we'll go ahead and use part B here. This is a mathematical induction. So let's go to the next page and actually verify that this formula is correct. And before we do that, just recall that what our value for S1 was, 1/2. So let's go to the next page. So we're claiming that Sn is n plus 1 factorial minus 1 over n plus 1 factorial. So we're using mathematical induction. First, we have to check the base case. When we plug in n equals 1, S1, let's plug it into this formula here. You get 2 minus 1 over 2 factorial, which is 1/2. And that agrees with the value of S1 from the previous page. So that checks out. Then we have the inductive step, where we go ahead and suppose that this equation is true for some value. Let's call it k. So I'm using k. So k is just some particular value of n for which this equation is true. And now I'd like to show that this is also, we have a similar formula for sk plus 1. So on one hand, sk plus 1 is sk plus ak plus 1. You take the previous partial sum and then you just add the newest term. And now I can describe sk using this formula from our inductive hypothesis. So this is k plus 1 factorial minus 1, k plus 1 factorial, and then minus, and then ak plus 1. Well, I already have a formula for a, k on the previous page. On the previous page, we know an is n over n plus 1 factorial. So use that formula with n equals k plus 1. Now we have this new expression here. We would want to simplify this. Eventually, what we want is this. We want this formula to still be true when we replace k with k plus 1. So after we replace it on the left, then on the right-hand side, this is what we have. So that's what we want to have for sk plus 1. So we started with sk plus 1 over here on the left. We're using the definition of the partial sums. We'll simplify this, and eventually we want to end with this expression over here in the blue. So we're almost there. We have a few steps left. Let's just combine these fractions. Yep. K plus 1 factorial minus 1. And then there's k plus 2. And then plus k plus 1. All over k plus 2 factorial. So all I did here was multiply top and bottom of the red by k plus 2. And then we can go ahead and simplify this. So if I multiply that k plus 2 on the inside, that becomes k plus 2 factorial. And then I have minus k plus 2 and then plus k plus 1. So that's just distributing the k plus 2 to the negative 1 as well. All over k plus 2 factorial. And then just simplify that numerator. Minus, and then just the k's cancel. We have minus 2 plus 1, so that's minus 1 all over k plus 2 factorial. And yes, this is exactly what we wanted. This means that the formula is still true when we replace k from our hypothesis with k plus 1. So that verifies part B that our guess that our formula for Sn was correct. Now let's go ahead to do part C. So for part C, we have that it's convergent. They're telling us to suppose that this thing converges. So let's write this as a limit of as n goes to infinity. Let's not use n, let's use a different letter there. Let's say k goes to infinity of sk. So we're taking the limit as the partial sums. However, from part B, we just found the formula for sk. That was k plus 1 factorial minus 1 over k plus 1 factorial. So this is just from using part B to go from here to here. Then this limit can be evaluated, but it might help to rewrite this by, let's go ahead and divide top and bottom by the denominator. So when we do this, or in other words, just split this into two fractions. So we have one fraction that when they cancel out, minus 1 over k plus 1 factorial. And then as we take the limit, this denominator gets really, really large in the limit. So the fraction goes to 0 because there's only a 1 up there. And then we just have 1. And that's the sum of the series. And this is our final answer.